Good afternoon, everybody. If you can hear me, please raise your hand so I know. Excellent, excellent, excellent. 22 persons already. Thank you very much. Thank you. 40 persons already. Thank you very much. Thank you. You're welcome once again to another webinar session powered by Beina Capability Academy. My name is Malam Ibrahim Lawal. I will be your host once again today. Good morning, good afternoon, good evening, from wherever you may be joining us today. We're gradually having and getting global audience, and that excites us. Thank you all of you for the support that you have shown us by joining our webinars every time and every day. Before we go to the topic of today, I would like to run through some very important information for all of us. This webinar of today will be recorded and it will be sent alongside the slides and the question and answer responses to everyone who has attended. I note again, the webinar recording, the Q&A responses, and the slides shall only be sent out by tomorrow or next to those who attend, not those who register. Only to those who attend. So if you have your friends who registered but have not attended, please call on them to join us as quickly as possible. This webinar is a free webinar, and as such, it does not come with a certificate. However, a certificate is available for a token fee of 2,000 Naira, and that is about $5, 2,000 Naira. So after this session, if you require a certificate, please chat any of our numbers you will see in this presentation, the very last slide in this presentation, or you go to our website, all our numbers are there, or go to our social media accounts, all our numbers are there, and you indicate that you want a certificate. You pay the fee of 2,000 Naira and you will get a certificate immediately. This is true for only free webinars. Our paid webinars will come automatically with the certificate, absolutely free. You don't have to pay for that. During this webinar session, if you have any questions related to the topic of discourse today, we will urge you to please drop the questions in the Q&A panel, in the Q&A pane. Please do not drop your related questions in the chat pane, because the chat area is usually rowdy. So if you want your related question to be answered, please drop in the Q&A pane. Then every other discussion can be in the chat pane. We urge all of you to please follow us on social media. If you can see my cursor, we have our YouTube icon here, Facebook, Twitter, Instagram, and LinkedIn. Please follow us on social media for updates so that you do not miss any updates. Many of you have followed us in the last 1 month that we have been doing webinars, but it's just a fraction of the population that registers for our webinars. But we need all of you, please, to follow us on social media. You can do it right now before we even start the webinar. But if you cannot do it right now because you are using that particular device for this webinar, please note it down on a paper somewhere so that immediately after this session, you can go and follow us on social media. We have been telling you that we are preparing our ELMS, our Learning Management System portal, and we're happy to tell you that alpha testing of that ELMS portal has started yesterday. We are fixing bugs, we're testing, and we want to do the best that we can so that once we launch it later in July, you will have the best experience of your time. Beta testing will happen by the end, will start by the end of first week of July. And hopefully, we are hoping really that before the end of July, that ELMS portal will be running and you can take your courses completely virtually and at a much lower rate. At the end of this webinar, I shall be informing you again of our upcoming webinar. One will be a free webinar coming directly and immediately next weekend. And the other one will be a paid webinar, which will come up on the 27th of June. I will talk about this and more at the end of this webinar presentation. Once again, I thank all of you for joining us from wherever you are around the world. Good morning, good afternoon, good evening. I will hand over controls to our speaker for today, Gado Yakubu Titus. He's somebody that many of you already know. He's a senior manager for production and capability development at Chi Nigeria Limited. He's a very, very good friend of the house, very knowledgeable, very brilliant young man, excellent guy, and a very strong supporter of the Beina strategy. Please welcome Gado Titus. Gado, if you can hear me, please take control. And
yeah, I can hear you, madam. Okay, good afternoon, everyone. My name is Gado Titus. Okay, so I'll be taking you through today's webinar session. We're going to be talking about machinery failures, the building block of asset reliability. Here you can see a picture of a turbine, a failed turbine. Now, you can imagine the size of this turbine, and you can imagine the what the company or what the organization will have to go through to fix this. That is, if they can actually fix this. It's going to take a lot of effort, it's going to take a lot of resources, and a lot of time to even get to fix this. Now, this is one of the reasons why you as an individual, as a company, must ensure that you avoid failures. And to be able to avoid or prevent failures, you must first of all understand what failure is and what failure analysis is and what you need to do to ensure that failure does not occur. Very important. Today I'm going to be talking about so many things. Some you know, some you don't know, some you may agree with, some you may not agree with, but as I proceed in the session, it's going to become clear. The cobwebs and all that are going to be clear. So let's proceed. So today we're going to be looking at definition of failure-related terms. We're going to be looking at types of failure. We're going to be looking at failure patterns. We're going to be looking at failure modes versus failure mechanisms. They look similar, but they're actually different. We're going to be looking at failure modes, effects, and criticality analysis, also known as FMEA. We're going to be looking at maintenance strategies originating from failure analysis, which is a part of RCM. RCM is reliability-centered maintenance. We're going to be looking at failures versus maintenance strategies versus safety. Okay, so before we proceed, I want to ask a question, and I want everybody to answer. I'll just give us 2 minutes. What do you think, or what do you know failure to be? What is failure? You can just type in the chat section, what is failure? I'm going to pick just 2 responses and then we'll proceed. What is failure? 2 minutes. Okay, failure, inability of an equipment to perform according to requirements. Somebody says loss of function. Somebody says failure is the loss of function of an asset. Failure is the inability of an equipment to meet demand. Good responses. The ability of machines not to pass NDT. Good, 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 good. Okay, let's proceed. What is failure? Failure is the inability of an asset to perform one or more of its intended function. The inability of an asset to perform one or more of its intended function. Now, let's go to function. Function is defined as the purpose for which an asset is designed. This is first defined by the OEM, but most often redefined by the user. By the way, OEM means original equipment manufacturer, or better still, you could say designer. So, an asset can be said to have failed only if it is unable to perform its intended function as defined or as determined by the user of the asset. What do I mean? Now, I am a designer and I designed a bicycle. And for my design, I have designed that that bicycle should be able to carry just one person. One person. Now, you as a user buys my bicycle and you say, no, I don't want to use this bicycle to carry one person. I want to use this bicycle to carry two people. Now, the function of that asset has changed because the designer designed the bicycle to carry one person, but you are using the bicycle to carry two people. So your expectation from the bicycle is that you are able to carry two people, right? So until you get to a point you are unable to carry two people on that bicycle, you will not say the bicycle has failed. I don't know if I'm making sense. Now let me go to the next slide. From the next slide, I will be explaining primary function, and I'll be explaining primary function and I'll be explaining what secondary function is. So I'll be explaining this and this in the next slide. Now, I have two phones. I have a Nokia 3310 and I have a Samsung S20. For me, my Nokia 3310 is for phone calls. But my Samsung S20 is for photographs and for social media. I want to be able to take photographs with my Samsung S20. I want to be able to surf the internet with my Samsung S20. Now, if I am unable to make phone calls with my Samsung S20, it doesn't matter to me because that is not the function of the Samsung S20 as defined by me. Yes, Samsung S20 has the capability for phone calls as designed by the manufacturer. But for me, I bought this Samsung S20 so I can be able to take photographs and I can be able to surf the internet. So until I am unable to take photographs with my Samsung S20 or I am unable to surf the internet with my Samsung S20, I cannot say my Samsung S20 has failed. I believe I'm communicating. Now, for my Nokia 3310, the primary function of my Nokia 3310 is to be able to make phone calls. So as far as I'm making phone calls with my 3310, everything is fine. The only time I can say my 3310 Nokia has failed is when I am unable to make phone calls with it. Now, let's go back to primary functions and secondary functions. Generally, the primary function of a phone is to be able to make and receive calls. However, over time, due to technological advancement, due to digitalization, your mobile phone is now like a mini computer where you can do so many other things with it. But the primary function of your mobile phone is to be able to what? Make phone calls. The secondary function of your mobile phone as defined by the OEM or the manufacturer is to be able to take photographs, listen to music, edit photographs, you'll be able to surf the internet, and so many other functions. So an asset could have multiple functions, but we must be able to first of all define what the primary function of that asset is. Very important. Because until you're able to define the function of an asset, you cannot be able to judge whether an asset has failed or not. These are very important definitions and basic background that we need to understand from the beginning. Good. Now let's proceed. What is reliability? Reliability is defined to be the probability that the component, system, or asset will perform its required function as defined by the user. Note the word user. User is coming in now. For a given period of time under stated operating conditions. If you look at the definition, three areas are highlighted. Let me use my cursor to highlight this. 3 areas are highlighted: required function as defined by the user, period of time, and then operating conditions. It is absolutely impossible to define reliability without these terms. So you can define reliability anyhow you want it, but these 3 terms must be part of the definition: required function as defined by the user, period of time, and then operating conditions. Now, these acronyms, MTTF and MTBF, are measures of reliability. We're going to see them as we proceed in our definitions. Now, the reliability of an asset can be achieved throughout the equipment life cycle. That is from design stage to fabrication, to installation, for operation and maintenance, and to decommissioning. And we must note that decommissioning does not necessarily mean the end of life of an asset. An asset can be decommissioned from point A and reinstalled in point B. Very important to note. So when we say an asset is being decommissioned, it does not necessarily mean that the asset is no longer useful or the asset has come to its end of life. So reliability can be achieved anywhere between design and decommissioning of an asset. Very important. Or design to end of life of an asset. It's very important to note this. So during design, you can achieve reliability. During fabrication, you can achieve reliability, because if you do not fabricate well, you will lose reliability even from fabrication. If you don't install well, precision installation, you will lose reliability even from installation. And that is one major challenge many organizations have today. When they go for FAT, reliability of an asset is 98%, for example. After installation of the asset at the point of use, reliability of the asset becomes 80%, for example. What has changed? The only thing that has changed is installation. It means something has gone wrong during installation, or the operating conditions of the asset at the point of use does not necessarily match its design operating conditions. This is very important to note. Okay, so this mathematical model here is the model or the formula, let me use that, for reliability. R of t is equals to exponential minus lambda t. Lambda here is failure rate, and t here is operating time. So reliability, basic reliability can be broadly categorized into 2. Reliability in series and reliability in parallel. And all these are found under what we call RBD, reliability block diagrams or reliability models. Now, let me say this here also. The reliability of an asset or a system is a function of the reliability of its component parts. So, the overall reliability of a system is determined by the reliability of the component parts that makes up the system. That is why it is very important to understand the architectural build-up of your system. Because if you don't understand this, you will not be able to determine the absolute reliability or operational reliability of your asset. So for reliability in series, for those of us that are electrical engineers, you know resistors in series. When you draw that electrical circuit diagram and you put your resistors in series, that is how your reliability in series looks like. When the reliability of your overall system is dependent on the reliability of each of the component parts. For example, if one fails, if a component fails, it affects the overall reliability of the system. We can say that reliability configuration is a series configuration. And this is the mathematical model for that configuration. R of S is equal to R1 times R2 times R3 times R whatever up to Rn. That is what is called system reliability for series. Then for parallel, this is the mathematical model for parallel, whereby it depends on the configuration. We have what is called active reliability and passive reliability. I don't want to go into that. M out of N reliability, that is a little advanced. But for basic reliability, we have a reliability in parallel, and this is given at this with this formula. So if you have system comp or system 1 or subsystem 1 with reliability of R1 and subsystem 2 with reliability of R2, and the configuration is a parallel configuration, this is the formula you use to calculate the system reliability. RS here stands for system reliability. Okay, so let's proceed. Okay, failure rate. Failure rate is defined as the number of failures per unit time. And failure rate is also known as lambda. Whenever you see lambda in reliability, they are making reference to failure rate. And this is a mathematical model for failure rate. Number of failures divided by total operating time. Very important. And failure rate could also be the inverse of mean time between failure. We're going to see this later, or inverse of mean time to failure. Let's look at this example. 20 air conditioning units designed for use in NASA space shuttles operated for 1,000 hours. One failed after 200 hours and another failed after 600 hours. Now, we are going to be looking at failure rate in percentage. I'm going to be looking at failure rate in number. Now, for failure rate in percentage, you're going to look at the number of failures, which is 2, divided by number of units in the experiment, or number of units under test, or number of units in the mission, which is 20. Then you multiply by 100 to make it a percentage. So 2 divided by 20 multiplied by 100 is going to give you 10%. So failure rate of this system in percentage is 10%. Now, failure rate in number. Yes, 2 here is number of failures divided by 20,000 here is 20 units multiplied by 1,000 hours. So this is supposed to be your total operating time, but you cannot just use this as total operating time. And this is because you started with 20 air conditioning units, but you did not end with 20 air conditioning units because 2 air conditioning units failed before the end of mission, or end of experiment, or end of test. Now, how do we come about this 1,200? One failed after 200 hours. Remember, the experiment is supposed to be for 1,000 hours. So 1,000 subtracting, when you subtract 200 from 1,000, you have 800. So the total time that this one was part of the experiment was just 200 out of 1,000. So you keep 800 aside as non-operating time for one of the air conditioning units. And then you do the same for the second air conditioning unit that failed after 600 hours. You take away 600 from 1,000 hours, you get 400. So when you add 400 plus 800, which is going to give you 1,200 non-operating time, you will subtract that from the total of 20,000 expected operating time. Now remember, this 20,000 is assuming that all 20 air conditioning units were alive throughout the period of testing, but of course they were not. So you subtract 1,200 from 20,000 to get 18,800. So when you divide 2 by 18,800, you get this. This is your failure rate per unit hour. Very important. So this is how they come about this failure rate per unit hour. And remember, we said failure rate is equal to inverse of mean time between failure. So when you invert this, you get this. This is now your mean time between failure, which is 9,434 hours. So I believe this is clear now. Number of failures divided by total operating time is failure rate. And failure rate is equal to inverse of mean time between failure and inverse of mean time to failure. I'm going to explain the difference between this and this as we proceed. Okay, now mean time between failure. This represents the average time between failure events over a specific period of time. What this means is, in the next 10 hours, how many times does this asset fail? Now, I'm going to use this graphic to explain this. So let me bring up my cursor again, or my spotlight. Now, your asset at this point is off. When you turn on your asset and it starts operating, it comes up and operates for a period of time, and failure occurs here, and your asset goes down. You take this time to fix your asset, and then after fixing the asset comes up again, uptime after repair, and it runs for a period of time, and then failure occurs again, your asset goes down, and then you repair again. After a period of time, you finish repairing, it goes up and operates for a period of time, and failure happens again, it fails and comes down again, like that. Now, remember, MTBF is also known as uptime. So mean time between failures is the mean of this time, and this time over the period of testing, or over the period of your consideration, over a specific period under consideration. So the mean of this, and this is what is called your mean time between failures. And the mean of this, and this is what is called your mean downtime. Your mean downtime is different from your mean time to repair. Your mean time to repair is a subset of your mean downtime. Okay, so let's proceed. Now, I've explained this in the previous slide. This is the relationship between mean time between failure and failure rate. Remember, anywhere you see lambda, it represents failure rate, which is total operating time divided by number of failures. If you invert this, what you are looking for is now failure rate. I believe that is clear. Okay, so let's proceed. Mean time to failure. Mean time to failure represents how long a machine is expected to run before it fails. Now, let me explain the difference between mean time between failure and mean time to failure. The difference between mean time to failure and mean time between failure is that mean time between failure is used for only assets that are maintainable, while mean time to failure is used for assets that are not maintainable or assets that are not repairable. Or better still, mean time to failure can only find application for assets that have only one mission life. What does this mean? Your light bulb now, if your light bulb goes bad, you cannot repair it and fix it back. So the end of life for that asset, your bulb, is when it fails. That is why you can see from the formula here, total operating time divided by number of failures. But this time around, number of failures is equals to 1, because you cannot have more than one failure, because you cannot repair the asset. You cannot fix the asset and bring it back to operation. So after one failure, the mission of that asset ends, and that asset has come to the end of life. Just like your rocket, mortar rockets, for example, they have just one life. After their mission, they end. It comes to an end of life. But thanks to Elon Musk, that has made a very outstanding invention of rockets that can go, execute a mission, and still come back to Earth. Then mean time to repair is the mean time to repair a failure, and represents the time it takes to fix a problem and get assets operating. So this talks about the time it takes to fix a failure. It has a lot of components. There's what we call the range time. I don't want to go into that. There's what we call the troubleshooting time. There's what we call the logistics time. There's what we call the administration time. All the summation of all this time is what makes up your mean time to repair. Remember, I said mean time to repair is a subset of mean downtime. So mean time to repair plus ramp up time is equal to mean downtime. It's not in this slide, but you can just get that. So, and it's given as sum of unscheduled downtimes divided by number of repairs. Sum of unscheduled downtimes, downtimes that are not scheduled, downtimes that are as a result of failures, divided by the number of repairs. Remember, it is not all failures that requires repair. Let me give an example. I'm a filling machine operator. I will use a bottling example most times because I work in the bottling industry. I'm a filling machine operator. Cap hooking on your filling machine stops the filling machine intermittently. True or false? True. But you don't repair anything. The only thing you need to do is just to hit the cap chute or whatever, and then cap starts coming again. So it is a failure, but you did not carry out a repair. I don't know if I'm making sense. So that is a typical example of failures that do not require repair. Okay, availability. Availability is defined as the probability that a component or system is available to perform its expected function at a given point in time, t, when required. Very important. There's a difference between this definition and the definition of reliability. Most people tend to mix it up. This is measured at a given time t, while reliability is measured over a period of time. It's very important to note this. I need to start my machine. I want to always come and press start. I want to push the start button and my machine responds appropriately. But when I push my start button and the machine does not respond, I cannot say that machine is not reliable. It may not be available at that point in time t, but I cannot say it is not reliable. I don't know if this is clear. So availability is equal to uptime divided by total time, and can also be given as mean uptime. That is mean. Remember, I talked about mean uptime in my explanation of MTBF. Mean uptime simply means mean time between failure, divided by mean uptime plus mean downtime. I talked about mean downtime also in my explanation of mean MTBF. So it's also given as MTBF divided by MTBF plus MDT. MDT means mean downtime. Very important to note. Then downtime is the active scheduled time during which the system is not available, not in an acceptable operating condition, and not performing the intended functions due largely to failures. What this means is that I have scheduled my asset to run for 18 hours. So the active scheduled time for that asset to run is 18 hours. So anything that makes that asset not to run within that active scheduled time is what is called downtime. Or any stoppage of that asset within that active scheduled time is what is called downtime. And this is largely caused by failures. I hope this is clear. Also, let's proceed. Types of failure. In my last webinar, I breezed through these types of failure and I used an example. I will still use the same example today. I'll maybe use the example of my phone, since I started with example of phones. Now, we have 4 major types of failures. We have what is called inherent failures. We have what is called the potential failures. We have what is called the functional failures. We have what is called the fatal failures. Some people call it total fatal failures. Some people call it catastrophic failures. Whatever you want to call it, but that is the failure. And this, at this point, your asset has totally broken down. So let's look at inherent failures. Inherent failures here at this point. Now, this graphic is trying to show us the condition of an asset over time. Condition of an asset over time. Now, here is the point where failure starts to occur. This failure is not necessarily age-related. For example, I just bought a phone today, brand new S20. Fantastic. Everything is working. But it's possible that there is a component in that S20 that has begun to fail. I may not see it. I may not know it's there, but it is there. Because over time, it will show. And it may not necessarily be over time. It could even happen immediately. It could happen just now. As I'm holding it now, it could just fail. You understand? So inherent failures are failures that come by design. They are in there by design. The next kind of failure is what is called potential failure. Potential failure, at this point, you can find out that it has started to fail. Now, I bought the phone, Inherent failure says there is a component in this phone that may likely fail. Potential failure says it has started failing. I can see that it has started failing, even though it has not started affecting the functionality of the phone, but I can see that it has started failing. That is potential failure. Functional failure is when that component begins to affect the functionality of the phone. For example, the screen starts seizing now. Remember, I told you in the beginning that my S20 is used for photograph and for surfing the internet. So once the screen of my phone starts failing, it means I can no longer take photographs and I can no longer surf the internet. So it has failed because the functionality of that phone as defined by me has begun to be affected. So functional failure says it has started affecting the phone. My screen is beginning to go blank. Fatal failure is when my screen goes blank completely and I can no longer use the phone for the reason why I bought it. That is what is called fatal failure. I believe this is clear. Let me go back. Let me use a human being as an example again. I'm standing here talking to you, delivering this webinar. I'm okay. My performance is okay. I don't have headaches. I'm feeling very okay. But nothing says that in the next 5 minutes, I may not begin to have headache. That is inherent failure. So it is the probability of having headache is inbuilt, is in me by design. The probability of having stomach ache in the next 2 seconds is in me by design. That is what is called inherent failure. Potential failure is when I begin to have headache. I will still keep talking to you, I will still keep delivering my webinar, but I am having headache. That is potential failure. Functional failure is when I am unable to speak to you or deliver this webinar. Or maybe I deliver the webinar, but I deliver it in a certain way that I shouldn't have delivered. Or a certain way less than expectation. That is functional failure. It means the failure has begun to affect my performance, even though I have not broken down completely. Fatal failure, catastrophic failure, total fatal failure is when I am on the sick bed. I am no longer able to talk. I'm no longer able to move and all that. That is fatal failure. So I believe with this I've explained inherent, potential, functional, and fatal failure. Very important to know. Thank you. So let's proceed. Failure patterns. Now we have 6 major failure patterns as discovered by Nolan Heap. And these 6 failure patterns are the bad top curve, the wear out failure pattern, the fatigue failure pattern, the initial break-in failure pattern, the random failure pattern, and the infant mortality failure pattern. What this means is majority of assets fall into one of these 6 failure patterns. The way your asset will fail, whatever kind of asset it is, falls within one of these 6. And from here, you can see that bad top curve accounts for approximately 4% of failures. Wear out failure pattern accounts for approximately 2% of failures. Fatigue accounts for approximately 5% of failures. Initial break-in accounts for approximately 7% of failures. Random failure pattern accounts for approximately 14% of failures. Infant mortality failure pattern accounts for approximately 68% of failures. I'm going to explain each of these failure patterns in the next slide. But let's look at this. Graphic here. Now, bad top, wear out, and fatigue failure patterns are age-related, and they account for 11% of failures of different types of assets. While initial break-in period, random, and infant mortality account for 89% of failures, and they are non-age related. That is why it is very unprofessional for you as an individual or as a maintenance professional, as an operations director, to tie the performance of an asset to age. You understand? It is not professional when carrying out an RCA to say that one of the reasons why an asset failed is because of age. No, It is not always true. In fact, only 11% of assets fail due largely to age. 89% of asset failures are not related to age. So you cannot say based on just 11% that the reason why this machine is behaving like this is because it is old. There is nothing like a machine is old. There's nothing like that. There are lots of things you can do and you should do as a maintenance professional to ensure that your machine is new every day. Very important. So let's proceed to the explanation of these various failure patterns. Failure pattern A, which is our bad top failure pattern, is known as the bad top curve and has a high probability of failure when the equipment is new. So what this means is, at this point, the equipment is new. At this point, this is the end of life of the equipment. So at the beginning, when the equipment is new, the probability of failure is high. After some time, this stage is called the infant mortality stage. At the beginning, the probability of failure is high. As you begin to use the asset, the probability of failure drops down and gets to a constant stage. And at the end of life, there is a sharp increment in the failure probability. Failure probability increases immediately. So only 4% of assets have this kind of failure patterns. Now, the next one is the wear out curve. It consists of a low level of random failures, followed by a sharp increase in failures at the end of its life. What this means is this: at the beginning of the life of the asset, failures are constant. By this, it means failures can happen at random. But at the end of life of the asset, the failure probability goes high. That means the failure rate of that asset increases. The failure rate before was 1. Failure rate can be 2, 3 at the end of life here. It means the asset is beginning to wear. This happens most times to mechanical assets due to wear and tear. Now, let's look at failure pattern C. It's known as the fatigue curve and is characterized by a gradual but increasing level of failures over the course of the equipment life. This is it. There is a gradual but consistent increase in the failure rates of the asset, or in the failure probability of the asset. So at the beginning, failures are minimal, but the asset begins to age, failure rate increases. So these 3 types of failure patterns are age related and they account for only 11% of failures. Now let's go to the next 3. Failure pattern D is known as the initial break-in curve and starts off with a very low level of failures followed by a sharp rise to a constant level. This is it. At the beginning of the life of the asset, there is a very low probability of failure. But as it begins to, as you continue to use the asset, failure rate increases, but it gets to a stage where it becomes constant and remains constant till the end of life of the asset. And this accounts for 7% of overall asset failure. The next is failure pattern E, which is the random failure pattern. And for this one, it enjoys a consistent level of random failures over the life of the equipment with no pronounced increase or decrease related to the life of the equipment. So it means that throughout the life of the asset, the failure rate of the asset remains constant. It can happen at any point in time. This is most likely applicable to your electrical components or electrical assets. So failure pattern F, which is known as the infant mortality curve, it shows a high initial failure rate followed by a random level of failure. What this means is, at the beginning of life of the asset, the failure rate of that asset is high, or failure probability is high. As you begin to use over time, it gets to a constant level and remains constant throughout the life of the asset. This could also find application for electrical components or electrical assets. For example, if your asset does not fail at the beginning of the life, it means you are going to enjoy that asset till the end of life. Like your television sets now. If at the beginning of life of that asset, it doesn't fail, that means it will not fail over a period of time. So let's proceed. Now, at this point, I'd like to invite Malam to take up some polls before we go to the second part of this presentation. So over to you, Malam.
Okay, sir. Okay, sir. Let's take this poll. And let me allow panelists to also vote. The poll is up. Please vote. There are 156 of us. Please vote. Only 4 people have voted. 20, 30, 50. We have 156 persons here. Only 80 have voted. Just 50%. Very poor. I'll give you 5 seconds. 5, 4, 3, 2, 1, 0. Thank you. Gado, can you see the results?
I can, Malam.
You can or you can't?
I can.
Okay. Okay. The result clearly shows that a majority of the participants here do some form of failure identification and failure analysis. 48% of respondents say they do failure identification and analysis sometimes. A good population, 26% or 31% say they do this always, which is very good, very, very good. Yeah. And then some say they don't do it. They don't do it at all. They don't do it this way. They have never done it. A combined population of 26%. And in absolute number, 31%. These people, these 31 persons have need for improvement, immediate need for improvement. So they can continue to engage with us and continue to stay glued to our social media channels to attend more and more free webinars to learn more. You are obviously in the back seat. This is 2020. You're obviously in the back seat. But the good news is that we are here to help you bridge the gap in your knowledge. Thank you very much. I will share the next post now. I'll stop this one. And the next post, the next poll is this. I have flashed it. Please vote. Zero votes, 1 vote, 3 votes. Only 60 people have voted. We are 158 at this moment. I'll stop in 5 seconds. 5, 4, 3, 2, 1, 0. Thank you. And I will share the results. A very brilliant outcome. 64% of the respondents say potential failure is the correct answer. Potential failure is the correct answer. And I will agree with them. Potential failure will be the correct answer. So a combination of inherent and potential failure will do you very well, very good in preventing asset unreliability issues. Functional and fatal failure, I'm sorry, the failures have already happened. They have degraded your asset to a lower performance level or 0 performance level, so they will not help. So the 27 combined percentage who have chosen this, they are not correct. One more poll, Gado. One more poll. Now, please vote. This is the last poll for this presentation topic. We have 2 more polls, but not related to this presentation topic. Vote, vote, vote. Only 10 people have voted. Somebody said he's not seeing any poll. Let him wear glasses. Oh. All right, I will stop the poll in 5 seconds. 5, 4, 3, 2, 1, 0. Thank you very much for attending to this. Thank you. All right. So, overwhelming percentage of the respondents say, that's 46%, they say no, that these 2 measures are not the same and they are not interchangeable. 46%, that is 59 absolute numbers, say these 2 measures are not the same and are not interchangeable. That is not exactly correct. The correct response will be the third one. They are not the same, but they are interchangeable under some conditions. They are not the same as Gado has defined, but they are interchangeable. So 27% and 37 of us in this group have gotten this correct. For the 46% who did not get this correct, that means that they still have a little bit of cloudy understanding of what these 2 things mean and how they relate.
Yes, madam, I will just highlight a little about it as I proceed.
Okay, good. So, but that is not a bad news. You only need to stay glued to us. This time and many more times, you will get to understand these relationships and how they work. But for this poll, we'll take the option 3, which 34 of us got. Thank you very much. You can continue, Gado.
Okay, sir. Thank you very much. Okay, so let me also give us a little highlight about this MTBF and MTTF. So remember I said failure rate is equals to 1 all over MTBF, right? For MTTF, it is not failure rate. Now you are forcing me to go into a little advanced reliability. It is called hazard rate. Failure rate is equal to 1 divided by MTBF. Hazard rate is equal to 1 divided by MTTF. Remember, I said for MTTF, asset has just 1 life, 1 mission life. MTTF is used for an asset that has just 1 life, 1 mission, like your sensors, your light bulbs, your rockets. Any asset that just has 1 life, you use MTTF for. But for assets that you can repair after failure and bring them back to operation, you use MTBF for. That is why number of failures is 1 for MTTF, and there is no limited number of failures for MTBF. Just like Malam said, they are not the same, but they can be used interchangeably. For example, I can give you a reliability problem that has to do with mission critical assets. For example, an asset that has just 1 mission life, and I will give you MTBF and not give you MTTF, and I'll ask you to look for hazard rate. What do? You will have to use the MTBF in place of MTTF. So a lot of literatures could do that. So they are not the same. It's very important to know the major differences between them. but you must also note that you can use them interchangeably. I believe that is clear. So let's proceed. Thank you for your polls.
Thank you.
All right. So we're going to zoom straight into failure mode and effect analysis. I know many of us have seen this FMEA before. I have been privileged to meet with people who I have asked what FMEA is, and the responses I get are not really satisfying because they understand FMEA as something else. But today you are going to get a full understanding of what FMEA is and how it finds application in your day-to-day life. I try as much as possible to give examples that you can relate with, give examples that you can use, something that is handy to understand. So what is FMEA? FMEA is a risk-based analysis method used for reliability analysis to reduce failure probabilities. Long grammar, Abi. 3 keywords: risk-based analysis, reliability analysis, failure probabilities. It is a risk-based analysis. By risk-based, you quantify, you are trying to eliminate risk, or you're trying to mitigate risk when you carry out FMEA for an asset, for a system, for a process, for a design, as the case may be. So FMEA is a risk-based analysis method used for reliability analysis to reduce failure probabilities. It is used before failure occurs, unlike RCA that is used after failure occurs. What does this mean? I buy a new phone today. It is brand new, it has not failed, it is still new. But I can carry out FMEA on this phone to know the various ways this phone can fail, and then I'll put in systems in place to ensure that this phone does not fail. That is FMEA. While RCA is, I am using the phone and a failure occurs, and I'm trying to look for the root cause of the failure to fix the failure and put systems in place to avoid a reoccurrence of that failure mode. Long grammar. As we proceed, we will get better understanding. So what are the objectives of FMEA? Number 1, it is to identify and fully understand potential failure modes and their causes and the effects of each failure on the system or the end users for a given product or process. What this means is, I have a phone, so I want to understand the various ways this phone can fail. One of the ways this phone can fail, my S20 for example, is the screen can go blank. It's a failure mode. The phone doesn't get network. It's a failure mode. My earpiece is not working. It's a failure mode. My mouthpiece is not working. It's a failure mode. So one thing that FMEA helps you to do is to identify all of these failure modes and put systems in place to ensure or mitigate the occurrence or reduce the likelihood of occurrence of these failure modes. That is number 1 objective of FMEA. Number 2, it assesses the risks associated with the identified failure modes, the effects of each failure mode, and prioritizes issues for preventive action. Just like I mentioned, after assessing the failure modes, assessing the effects of the failure modes, I will prioritize these failure modes and then come up with a system or strategy to prevent the occurrence of these failure modes. Number 3, it is to identify and carry out CAPAs. CAPAs means corrective actions and preventive actions to address the most serious concerns. And if somebody is wondering, why is corrective action coming here? Now, we have different types of FMEA. We have what is called the design FMEA, the process FMEA, and systems FMEA. These are different types of FMEA, and they find application in different areas. They are not the same. But that is a talk for another day. FMEA is a topic on its own. It's a course. It's a 3-day course on its own that Beina delivers. So if you want to know more about that, you can enroll for that course. So wondering why corrective action is here is because in design FMEA, as a designer, when I design a prototype or when I design or build a prototype, I will subject that asset to different types of failures or different types of stress. We have different types of stress. We have stress testing, we have degradation testing, we have demonstration testing, different types of testing. That's for advanced reliability. So I'll subject this asset to these types of testing so that I can know possible ways this asset can fail. And when I know possible ways this asset can fail, right from design, I can correct this to ensure that I save the user the stress of having to go through to bring in mitigation steps or mitigative actions to prevent these failures from occurring. So that is the reason why you can see CAPA here, corrective action. I've already mentioned preventive action in point number 2. That is why you can see corrective action in point number 3. So these 3 are the major objectives of FMEA. So what are failure modes? We are going to FMEA proper. A failure mode is any event which potentially causes a functional failure. Remember, we've talked about function in the beginning. We talked about failure in the beginning. So a failure mode is any event which potentially causes a functional failure. It is the best way to show the relationship and distinction between failed states and the event which causes them. And one of these ways to do this is to list functional failures first. So when I buy my phone and I define the function of this phone, remember from the beginning I said the function of my phone, my S20, is to be able to take photographs and to be able to surf the internet. The function of the phone has been defined. So the only time I can say this phone has failed is when it is unable to allow me take photograph or surf the internet. So when my phone is unable to surf the internet or allow me to take photograph, I have defined what functional failure is. So for this S20 as an asset, functional failure is inability to take photographs, inability to surf the internet. That is functional failure as defined by me, the user. Now, what are the things that can make me or make my phone not be able to surf the internet or take photographs? There could be plenty of them. Chief of them all is a cracked screen or a blank screen. When my screen is blank, that's the end. I cannot take photographs. If I take photographs, I'm just wasting my time. I cannot surf the internet. So a blank screen is a failure mode that can cause dysfunctional failure. That's one. Another failure mode is for surfing the internet. If my touchpad stops working, I cannot surf the internet. I cannot take photographs. I cannot even go to camera. That is a failure mode that can cause functional failure. Another failure mode is if the camera of my phone goes bad, I cannot take photographs. So it's a failure mode. Another failure mode is if I cannot have access to the internet, my phone doesn't get network. It's a failure mode. So all these are the different types of failure modes that can affect the functionality of this phone as defined by me. So one way to write out failure modes is this. First of all, you are going to write the parts, the problem, and the specific cause of failure. For example, a fuel pump bearing is a part. Seized is the problem. You understand? And this seized due to lack of lubrication, which is the specific cause of the problem. So when you want to write a failure mode, you can say fuel pump bearing seized due to lack of lubrication. I don't know if this is clear. Let me use my phone. My S20 screen went blank due to a crack or due to water ingress. I believe I'm making sense. So that is the explanation for failure mode. Let's proceed. Failure modes and mechanism. What is the difference? When listing failure modes, you should remember to include all failure modes that have occurred, all dominant failure modes that are likely to occur, failure modes that have occurred on similar equipment. These are very key. I don't want to talk about them. They are self-explanatory, so you look at them. So a failure mechanism is a detailed description excuse me, of a technical failure mode. Most failure mechanisms are physical degradation of components due to operational conditions combined with component features like design, material, and surface treatments. Let me save you all the grammar. Let me use my phone again, my S20. I love this S20. Okay, so screen goes blank is a failure mode on my S20. The failure mechanism for this failure mode is cracked screen. So the failure mode is screen blank, but the failure mechanism is cracked screen. There are two different things. The screen went blank because the screen has a crack. I don't know if this is clear. So let's look at failure effect. Failure effect describes what happens when a specific failure occurs. So when describing a failure effect, the following should be considered. What evidence, if any, to show that the failure has occurred? For example, my screen again. The only way I can know that my screen is blank is when I pick up my phone and I try to unlock and discover it is blank. I will know the failure has occurred. So it is an evidence. Blank screen is an evidence that this failure has occurred. In what ways, if any, it poses a threat to safety or the environment? That is for high-level machines that we use in the industries. In what ways, if any, it affects production and operations? That is for those of us in operations and production. What physical damage, if any, is caused by the failure? Now we're talking about failure mechanisms now. What must be done to repair the failure? So when you're talking about the effects of failure, you must consider these 5 points. What is the first thing I will see to know that a failure has occurred or this failure mode has occurred? It's very important. You must define this. They should be described in such a way to enable the maintenance team or operators to evidently see or know that a certain failure has occurred. For example, physical evidence like beacon lights. Most of our machines in the industries have beacon lights. When there is a failure, you don't need to be on the machine to know that there is a failure on the machine. Some of the beacons will begin to show red lights. Some of them show blue when they are okay, or blue when they are on standby, and green when they are running. So from afar, when you see red light on the beacon, you already know that something is wrong with this machine. That is one way to know that the failure has occurred. Other displays and smell and loud noise, but I will not encourage smells and loud noise because by the time it gets to smell and loud noise, the deed has already been done. And remember, we are trying to avoid this from even happening in the first place. So criticality analysis. In my previous webinar, I talked about criticality analysis. This is one way to streamline failure modes. So you can focus majorly on failure modes with very high priority or high RPN number. RPN numbers, let me explain what RPN numbers are. RPN means risk priority number, and it is a multiplication of severity, occurrence, and detection. What does this mean? If this failure mode occurs, how severe will it be? Will it lead to fatality? Will it lead to loss of production? Will it lead to loss of economic value and all that? That is how you measure severity. On a scale of 1 to 10, how severe will this failure be? Or will this failure be if this failure mode occurs? Occurrence is the likelihood or the frequency of failure. How frequent will this occur? Or how frequent does this occur? On a scale of 1 to 10, you will give the value. And then detection. Can I see how detectable is this failure before it occurs? If I can detect it on a scale of 1 to 10, I'll give it 5 or 10. High detectability. If I cannot detect it, I give it 1, for example. So when you multiply severity by occurrence by detection, what you get is what we call the RPN number. And it is this RPN number that will determine whether a failure mode is critical or not critical. whether you should focus on it or not focus on it. Now, for my phone, one failure mode for my phone could be failure of my mouthpiece. But failure of the mouthpiece of my S20 is not critical to me. Let's even leave RPN. I've not even done an RPN. The reason why it's not critical to me is because the function of the phone has nothing to do with the mouthpiece. You understand? So the RPN number helps you to prioritize your failure modes. Now, it is easy if you're talking about the phone because the failure modes may not be too much. But when you're talking about a very big asset that has thousands of component parts and has thousands of failure modes, it will be only wise to prioritize your failure modes and then focus on the ones that has high criticality. So criticality analysis, when you carry out criticality analysis on your assets or failure modes, what you are trying to do is to streamline your assets or streamline your failure modes so that you can know which one to focus on. Very important. So if you look at this, the right part, this graphic on the right part, it talks about equipment criticality, and this is determined by the RPN number. Of course, and criticality with very high ranking has a very high RPN number. And this is one mitigation strategy you can put in place. As you go down from very high, to moderate, to low, to very low, the ranking determines what you do to prevent the occurrence of that failure mode. Very important. So let's go to the next slide. Now, this is just, I put this on the presentation to show us an example of a design FMEA worksheet. Remember, let me bring up my highlighter. Okay, so remember we started with function of an asset. You cannot determine if an asset has failed or not failed if you don't define the function of the asset. So the first step is what? You define the function of the asset. The next step is what? You find out what the potential failure modes of the assets are. They could be 500, it could be 1,000, it could be whatever. The next step is what? Determine the potential effects of the failure. And then the next step is to define the severity of the failure or the failure mode if it occurs. Then you determine the potential mechanism of failure. Here we're talking about failure mechanism. Then you determine the likelihood of occurrence of the failure. Then the next step is potential design cause of failure mechanism. Then current design controls. What are the controls you are putting in place or that are in place currently? Then the next step, we talk about detectability. So when you multiply this by this, you get an RPN number of 192. But you don't stop there. To mitigate this, I need to come up with recommended actions. So when I come up with recommended actions and I determine who is responsible, when is it supposed to be completed and all that, and then when action is taken, this value is supposed to change. We have an RPN of 192. Of course, the severity of occurrence, if it happens, is 8. Of course, it will not change because if it happens, the same effect, the same consequence will still happen. Okay, so when you do all this, your new RPN number becomes 96. Of course, if you have if we put a failure mode with 192 RPN and you drop it to 96, remember we talked about this. Let me go back one slide and explain something. Remember, assuming at 196, you have here very high. Criticality is very high. When you put up your mitigation strategy from design and you reduce it from 196 to maybe 92, it can come down to low. So what you have succeeded in doing is putting up mitigation strategies that has reduced the risk level of a potential failure from very high to low. I believe this is clear. So that is the reason why I just added this slide. So let's proceed. So what is RCM? RCM is a technique used to determine the right maintenance strategies that will address failure modes and their effects, leading to higher availability and reliability and reduced risk and cost level. First of all, it is a risk-based cost-saving methodology you use to determine the most suitable maintenance strategy for your assets. In my previous webinar, I mentioned clearly that it is wrong practice to have generic maintenance strategy for all your assets. And the reason is because all your assets do not have the same failure modes. So you are going to treat your assets dependent on the type of failure modes your assets have. So the maintenance strategy you should apply for your assets should be a function of the types of failure modes that are peculiar to that asset. That is why it is very wrong practice to have a generic maintenance strategy for your asset. That is the reason why RCM is coming here. So RCM is just an addition of FMEA plus what we call RCM logic. We're going to see it soon. So in summary, RCM is a risk assessment tool. So it is driven first by safety before quantity and profit. Very key. Okay, so for RCM process, we've talked about almost everything here, but I'm going to just highlight it and rush to 6 and 7, which is the main focus. Remember, we talked about what are the functions of your asset. At the beginning, you determine the expectations from the asset as the user, and then set performance standards. The next, that's where you determine your primary functions and secondary functions, as the case may be. The next is, in what ways can it fail to meet functions? That's where you're talking about functional failures. Then the next, number 3, is what causes each functional failure. That's where you're talking about failure modes. The next step is what happens when each failure occurs. That is where you're talking about failure effects. We've talked about that. In what way does each failure matter? That is failure consequences. If this failure happens, what do I stand to lose? Will there be fatality? Will there be a loss of a machine? Whatever it is, you need to determine what the consequence of that failure is. Now, if you do from number 1 to 5, what you have succeeded in doing is carrying out FMEA. Then number 6, this is where RCM logic comes to play. After you determine what is the failure mode, what are the effects, what are the consequences of the failure mode, the next thing is, what should I do to predict or prevent this failure? This is where you are beginning to think of the best or most suitable maintenance strategy or mitigation plan. Mind you, your maintenance strategies, whatever it is, are supposed to be mitigative plans to ensure that you preserve the function of your assets. Very key. So number 6 is, what should I do to predict or to prevent the failure? When you start asking yourself these questions, what you are doing is what we call RCM logic. Number 7 is what the question you should ask is, what should be done if a suitable proactive task cannot be found? Okay, number 6, I'm looking for the best maintenance strategy to do, the best proactive task to do to prevent this failure mode from occurring. But number 7 is, what if I don't get, excuse me, what if I don't get this proactive task? What should I do? You have 2 options, either to run to failure or to redesign, but we'll see that in the coming slides. So broadly, when you are conducting RCM, you must keep this in mind. RCM ensures that all performed maintenance tasks are cost effective. So if your maintenance tasks after FMEA is not cost effective, what you are doing is not RCM. Then RCM contradicts the traditional perception that the reliability of equipment is directly related to operating age. I said this earlier. It is not professional to say the reliability of your asset is a function of age. It is, if you mention that it is 0 over 100, it is not related. Change your perception from today. It is not related. As a maintenance engineer, as a reliability engineer, it is your job to ensure that your asset is new every day. Very important. So the reliability of your asset is not a function of the operating age of the asset. You must note this when carrying out RCM. The number 3 thing is RCM focuses on preserving the functions of equipment or assets and not on preserving the equipment itself. This is very dicey but very key. As an engineer, as a maintenance engineer, as a reliability engineer, as an operations manager, as a plant manager, operations director, your job should be focused on preserving the function of the asset and not preserving the asset itself. What does this mean? You can preserve the asset and not preserve the function of the asset. It is possible, but it is impossible to preserve the function of the asset and not end up preserving the asset. And this is largely dependent on what you have defined the function of the asset to be. This is very key. Okay, so let's proceed. I know I'm already running out of time, but I'll try to round up. This is very broad, and most likely we will do a part 2 of this as Beina decides. So RCM can be looked at in 2 ways. You can look at RCM as a system. Let me bring out my cursor. You can look at RCM as a system, and you can also look at RCM for component-based approach. You can look at it as function-based approach for system and component-based approach for components. Let's look at it for function-based approach. First is to identify the system and the boundary limits. What is the system in question? The system in question here is my phone. What are the performance standards of this phone? This is where you come to system functions. What I'm expecting from the phone. What is the function of the phone as determined by me? The next step is identify system functional failures. In what ways or when can I say this phone has failed? I'm determining the functional failures of the phone. The next thing is what? Identify the failure modes. In what ways can this fail? Failure modes and their causes. Causes now has to do with failure mechanisms and the affected machine components for components. Then the next what is to describe or document the failure effects. After I have done this, the next thing to do is what? Come up with a decision diagram. This decision diagram is what is called the RCM logic, where I will identify the failure consequence categories and select preventive maintenance tasks with crafts and frequencies. After I have done this, I will sort and group the tasks to create a job plan and procedure. We have looked at it in a function-based approach. For component-based approach, I will do the same. Identify the components in question, set boundary limits, identify the major assemblies of the components, break down these to what is called sub-assemblies. There is a course also in Beina that is called, I can't remember the name now. When I remember, I'll tell you. Where we talked about, asset decomposition. The course is titled Asset Decomposition. You can be trained on how to decompose an asset from A to Z and then develop maintenance plans and strategies for a specific asset or multiple assets as the case may be. So you identify the major assemblies, identify the sub-assemblies, you do the same thing, identify the failure modes of the sub-assemblies or components. You consider worst case failure effects for failure consequences identification. After you've done this, the next is RCM logic, where you identify the failure consequence category, and then you select preventive maintenance tasks with crafts and frequencies. The last step is sort, group, tasks to create job plan and procedure. So from here to here, what you are doing is FMEA. Here to here, what you are doing is FMEA. What you are doing here is RCM logic. Very key. So let's proceed. So now still on RCM, failure analysis and maintenance strategy determination. The most appropriate equipment maintenance strategies can be determined by number 1, the failure pattern that applies to a given failure mode. If you understand the failure pattern of an asset, you can determine which type of maintenance strategy to put in place to prevent that failure from occurring. Very important. That was why we talked about failure patterns in the beginning. So for whatever asset you have, you must sit down and understand the failure pattern of that asset. Yes, you may not have enough failure data, but you can make research. Somebody has used that asset before you. You can ask questions around, okay, when you were using this asset, what is the failure history of this asset? So from the failure history of that asset, you can understand the failure pattern of that asset. And of course, when you understand the failure pattern of the asset, You can determine which maintenance strategy is best for that asset. The next is mean time between failure. If you understand the mean time between failure of an asset, you can predict the next time an asset is likely to fail. And if you can predict the next time an asset is likely to fail, you will most likely be able to put systems in place to mitigate that failure. For example, maybe a preventive action, a preventive maintenance action, maybe change of oil, as the case may be. Then the next is what failure mode and effect analysis. We talked about it. If you carry out FMEA for an asset, you can be able from that FMEA to determine the maintenance strategy best fit for that asset, which is what is called RCM. Okay, now let's look at these failures versus maintenance strategies versus safety. Still trying to use our PF curve to explain this, but it's a little dicey here. Here, the kind of maintenance you can do to catch this failure here, which is inherent failure, is what we call precision maintenance. Most of these maintenance activities are design related and can be applied during installation. When you do precision installation, you can catch this failure. Let me bring out my cursor. You can catch this failure here. Precision installation, where you use laser alignment, you check for thermal growth, you check for pipe strain and etc. So when you do precision maintenance here, you can catch this failure here. Here, because it is potential, it has started occurring and you can be able to detect it, maybe not with your physical eyes, but you can detect it with some tools like ultrasonic detectors, vibration analysis, oil analysis, as the case may be, as it is here. You can detect with ultrasonic spike, you can detect with vibration analysis, you can detect with oil analysis. So what you are doing, the kind of maintenance you can do to catch this failure here, potential failure, is what is called condition-based monitoring or condition-based maintenance / predictive monitoring. That is another talk for another day. There's a difference between CBM and predictive monitoring. They are not the same. Then the kind of maintenance you do to catch this type of failure, which is functional failure, is preventive maintenance. At this point, you are beginning to hear audible noise. You can feel the temperature of your pump or whatever going high. You can discover that there are mechanical loose parts that are dangling and all that. So the kind of maintenance you can do here to catch this kind of failure is what is called preventive maintenance. And the kind of maintenance you can do here is what is called corrective maintenance. The reason why it is corrective is because failure has already occurred. So what you are doing here is to correct it, to bring it back to functionality. And you can also do run to failure here, depending on the criticality or consequence of failure here. So let's relate it to safety. Here is unsafe acts and conditions. When your personnel begin to have unsafe acts and conditions, here you are beginning to have signs. You are beginning to have signs. You are beginning to have signs. So when you are relating this to safety, you are beginning to have signs. It's like you are beginning to see unsafe conditions. You are beginning to see unsafe conditions here. At this point, beginning of this point, it becomes near misses. When it gets to this point, it could cause minor injuries for operation staff. When it gets to this point, it could cause severe injury. And what we don't want is, we don't even want to get to this point. The best for us is near miss. Let it just stop at near miss. When it becomes near miss, we raise near miss forms and then they fix them and bring them back to this state of maybe unsafe or even before unsafe. So at the end of the day, everything we do in reliability is interwoven. You cannot talk about reliability without talking about safety, especially for mission critical assets. We cannot be talking about shit happens on aircraft. Shit should not happen on an aircraft, because if shit happens on an aircraft, a lot of lives will be lost. Shit should not happen in a nuclear plant, because if shit happens in a nuclear plant, a lot of lives will be lost. Very important. So this slide here is just an attempt to explain the relationship between failures, maintenance strategies, and safety. So if you look here, non-routine maintenance activity results in higher probability of injury. So when you don't carry out routine preventive maintenance activities, you have higher probability of injury. Very important. So let's proceed. Okay. So this is our summary. This is our last slide, and I'm going to explain this as a summary. Failure gives direction in asset design. What does this mean? During design, as a designer, I put my prototypes under different types of testing to expose different types of failures. And if I am able to expose these different types of failure, I am able to design a more suitable and perfect asset for my users to use. So without failure, I will not be able to perfect my design. Very key. Number two, failure is the starting point of system or component redesign. Now we have passed through the stage of design. The asset is already in use. But as I began to use the asset, I discovered that I always have issue in this area. And I have checked to see if I can fix this issue in this area. I discovered that there is no predictive task that can fix this. There is no preventive task that can fix this. And I cannot run this to failure. So the best thing I can do is to redesign the asset. I believe for those of us that work in industries, there are many times you will have to redesign asset. I've done that. I've had to redesign some assets in the past when I was working as an automation engineer. When you reprogram a machine as an automation engineer, what you are doing is redesigning the machine. Then failure, number three, is the strength of early equipment management. What does early equipment management mean? When I buy my phone, Samsung S20, I don't know what the failure modes are. I don't know. I don't have an idea. This is the first time I'm using this phone. But it's also possible that someone has used this phone before. So when I get the information from someone who has used this phone before, information like failure history, MTBF of the asset, reliability of the asset, availability of the asset, and all that, I can use that to better manage my new S20 phone. That is what is called early equipment management. So I need failure history or failure data of my new asset to be able to manage asset from the beginning of use. Number four, failure history is the bedrock of reliability improvement. This is very key. Without failure history, there cannot be reliability improvement. So it is very important, as if you have not been doing it before in your industry, and as I see across board, I see that many companies do not really track failure history. It's a bad practice. You should be able to track the failure histories of each of your assets, because this is what will determine your reliability improvement projects. Very key. Then number four, without failure modes, there will be no maintenance strategies. I've talked about this largely in the course of the presentation. So you need failure modes to be able to determine the right maintenance strategies for your assets. So I believe you see how failure or machinery failures have or has a direct relationship with asset reliability improvement. So you must understand failure modes, you must understand failure analysis before you can start talking about asset reliability improvement. So this brings us to the end of my presentation. I would like to hand over to Malam, the host at the moment. Thank you.
Thank you very much, Gado. Once again, you have delivered a very brilliant presentation. We appreciate your efforts. Please go to the chat and question and answer panes to continue to answer the attendees, as I have been doing all this while I close up. Thank you everybody for staying with us. Our time is almost up, but I will quickly again introduce, like we did last week, some of our super offerings. We are offering to you today the SMRP CMRT and SMRP CMRP global certifications at a very good price, because you are attending this session. So We're offering to you at 400,000 Naira against 450,000 Naira if you want to attend just the training. And the training is for 5 days. It's for 5 days. 400,000 Naira just because you have attended this webinar and a couple of others previously. If you have not attended at least 2 of our webinars, you shall not be entitled to this discount. So if you are interested in taking any of these certifications, CMRT or CMRP, then you should contact us and take advantage of this Super Saturday sale. Now, for the 400,000 Naira offer, it's just for training. So you will, on your own, pay your SMRP fees and pay your SMRP exam and membership fees. If, however, you want us to do it for you because you don't have time, you probably don't have a Forex account or you don't have ATM card, whatever. If you want us to do it for you, then you will pay a token fee of 650,000 Naira only, and then you will get everything included, everything. This super discount is only applicable to individuals. We do not give this super discount to companies, and for very good reasons, because companies usually pay after 30, 45, 60 days, and the cost of money is very high. So we cannot give this kind of super discount and then still wait for 60 days, 45 days to get our payment with all the deductions that come with it. So we're sorry to all our friends who represent companies here who may want to work with us. That is our concern. And you can see here our A-list CMRP and CMRT faculty. They're the best that you can get in the industry. These are the guys who are making it work. These are the guys who have made it possible for nearly 200 Nigerians and foreigners and Africans majorly to be certified CMRTs, CMRPs, CREs, CQEs. These are the main guys, led by the man on top. He's our boss. Our next webinar, which will be coming next week, is a free webinar. And it will hold next week, Saturday, June 20th at 2 o'clock as usual. The webinar will be presented by Aziz Olanio. He's a very good friend of the house. He works with Chevron, and he's going to bring some of his O&G experience to bear on this topic of defect elimination through bad actor investigation. So we're going to be dealing with eliminating defects, but through bad actor investigation. This is another way of saying RCA. Okay, so please join us next Saturday. The advert for this particular free webinar will come out most likely on Monday. We will blast email to all of you that have registered for this session. We have your email addresses. We are going to blast an email campaign to you, and we are also going to send our business development team will also send you all a WhatsApp message advertorial that contains the link to register for this session. Please make it a date with us on this day. There is a lot that you will learn. Our next paid webinar will be coming up on the last Saturday of this month. That is June 27th. It is a leadership course that will be led as speaker by Rafiu Abato, and my humble self will be supporting him. This session is paid, and it is for a token fee of 20,000 Naira, approximately $45 for everybody who want to come and learn leadership with us. The title of this particular leadership course will be Surviving Bad and Difficult Bosses series. It's a series, Surviving Bad and Difficult Bosses series, part 1, Not Fit for Command. It is a 6-part series that we will bring to you gradually. The first part will be 27th of June. I will be advertising this again next week when we hold the next webinar. That is Aziz's webinar. I will be advertising it again. Please join us. The advert for this paid webinar will be available immediately after today's session. Immediately after this session, we're going to blast an email, and our business development people will begin to reach you via WhatsApp. And so we all have time to register and make our payments. Now, unlike the previous paid webinar, this time around, when you register for this paid webinar, you shall not get an email with your login details. You shall not get immediately an email with your login details until we approve from the back end. And we will not approve from the back end unless you pay. So once you make your payment, we will approve your attendance from the back end. Only then will you get the login details into your mailbox. So pardon us and bear with us. That is how it's going to be. Please go and register. If you register, you will not get a login email immediately like you did during the registration for this particular webinar. The reason is because we have locked that. We will give approval individually from behind, and we'll only give approval to those who have paid. Once you pay, you get your login details to join us on that day. This is to prevent those who do not register from joining us. Thank you. Again, our previously advertised leadership training is a different leadership training from the one of 27th of June. Previously advertised leadership training, that is practical workplace leadership essentials that we had offered all attendees at 100,000 Naira, has been cancelled. That was to be a physical class. That has been cancelled. So we are planning to make this an online class on our ELMS. The ELMS is under construction, and like I mentioned at the beginning, we started our alpha test yesterday night, and it is still ongoing. So far, so good. By early July, hopefully we'll start the beta test, and hopefully we will not waste time on that. Once that is done, we're going to put this course online, and it will go for a token fee of 50,000 Naira only. 50,000 Naira only. It is a very good course. Watch out for it. We'll be advertising as well. We have taken your questions. We have been able to answer many of your questions as the presentation was going on. We still have many more. I can see up to 10 more questions available. We don't have much time anymore, so we apologize to all of you that we have not been able to take your questions right here, but you have not missed anything. Immediately after this session, we're going to download the questions. We're going to download the questions that you have sent to us. We will answer them and then send them back to you as our Q&A responses, as we do all the time. For any inquiries, our contact details are here as usual. Contact us by email or telephone, voice call, or better still, contact us by WhatsApp. All numbers are available. All numbers are available all the time. Contact us anytime that you wish from immediately now. This webinar has been recorded. Immediately after this, we are going to begin to render the video, prepare our Q&A responses, and then, of course, prepare this slide that you are seeing, make them PDF and send to only those who have attended. If you have not attended, if anybody who registered and he did not attend this session, that person shall not get the recorded resources. We want to encourage people to register and attend, not to register with the confidence that they will receive the materials after all. And we urge all of you who attend not to share your materials with them so that they can attend tomorrow. Thank you very much, everybody. We have come to the end of today's session. As I mentioned before, I greet you all from wherever you are joining us around the world. Good morning, good afternoon, good evening. My name is Malam Ibrahim Lawal. See you next week. Thank you.